Welcome back. In this lecture, we will introduce the concept of self-similarity. Self-similarity is different from the similarity that we've been discussing so far. In the similarity that we have developed up till now, it is the number of the independent parameters in a problem that get reduced. And because of this, we are able to model with uniquity parameters which are different from the original uniquity parameters. But in self-similarity, we deal with a reduction in the number of independent variables rather than the number of independent parameters. Typically, in many problems, we have two variables, one a space-like variable and one a time-like variable. We would see that there are cases where neither a characteristic length nor a characteristic time is specified in the problem. And because of this, it permits us to define a characteristic length in terms of a characteristic time or vice versa. We start with the example of the Stokes' first problem. This is a problem which is related to the fluid in the half space above an infinite plate. The fluid is at rest originally. At time t is equal to 0, it starts moving with a constant velocity v naught. In this situation, there are only two forces that are of interest. One is the unsteady force, the other the viscous force. The unsteady force, as usual, is estimated as mass times the acceleration rho Lc cubed times acceleration Vc divided by Tc, where C stands for the quantity being a characteristic quantity. Viscous forces, on the other hand, are like viscous stress, mu times the velocity gradient, Vc by Lc, times the area, which is Lc square. These two estimates result in a pi number, Lc square by nu Tc. Now, we can write the dependent variable as normalized by V naught, so that V of yt divided by V naught is a function of y over Lc, t over Tc, and this parameter Lc square by under root nu Tc. Now, there is no characteristic length and there is no characteristic time in this problem. If we take Tc equal to the current time t, then from this parameter should not be too small and should not be too big, because neither the viscous forces can be dropped from the equation nor the unsteady forces. This means this should be of order 1. And if Tc is like t, the current time, then Lc would be like under root nu T, where nu is the kinematic viscosity. And so this functional equation reduces to this function V yt divided by V naught is a function of y divided by under root nu t. From being a function of two independent variables y and t, we have reduced the equation to only one independent variable, which is a combination of y and t. This represents considerable advance. So we introduce eta as a lone dimensionless variable is equal to y divided by twice under root nu t. This factor of 2 is for the convenience, in the sense that if we introduce this 2 here, then the resulting equation is easy to solve. The normalized velocity then is v star is a function of eta. If we make the requisite transitions, then the equation del u by del t is equal to nu del square u by del y square, the governing equation for this flow, is reduced to f double prime plus twice eta f prime is equal to 0, with the boundary condition that f is equal to 1 and eta is equal to 0 on the plate, where the velocity is v naught, and f tends to 0 as eta tends to infinity. That's far away, the fluid is still at rest. This equation is readily integrated to give f is equal to 1 minus twice pi under root pi integral from 0 to eta e raised to power minus zeta squared d zeta. And this is recognized as the error function, or rather the complementary error function, ERFC of eta. F is the complementary error function of eta. This is the plot of this function. We have taken f on the horizontal axis and eta on the vertical axis. F decreases very sharply from 1 to 0 over a range for something like 0 to less than 2. Now, this is the normalized velocity as a function of eta. So if we choose a small time, then the velocity profile in the flow would look something like this. For a little larger time, this now is this, and so on for still greater time. I have drawn this profile by simply stretching the original profile in the y direction. As t increases, the value of y for identical values eta increases. That is accomplished by stretching the profile in the y direction. It is often convenient to talk about the penetration depth. The velocity jump at the plate reduces as you go up. At this value of y, at this time, the velocity is reduced to less than 1% of the velocity at the plate. We say that this is the penetration at this time. At a little larger time, the penetration is this. At this time, this is the penetration. We are now able to reduce a partial differential equation in two independent variables t and y to be an ordinary differential equation in a combined variable, independent variable eta. At eta is equal to 1.82, the value of f is about 0.01. This is saying that at eta is equal to 0.12, the value of v has reduced to 1% of the original perturbation at the bottom plate. Eta is equal to y divided by twice under root nu t is equal to 1.82 at this location. This gives us penetration depth to be 3.64 under root nu t. Let's consider one variation of this problem, this Stokes' second problem. In this case, the fluid is initially at rest, and then the lower plate starts moving sinusoidally, so that its velocity is given by v is equal to v naught sine omega t. Here again, the unsteady forces and the viscous forces are of significance, and in the same manner as we did before, we obtain the pi number LC square by nu Tc. Now, since both kind of forces must be there in the flow, none of these forces can be neglected. This parameter is of order 1. The characteristic time can be taken as 1 over the circular frequency omega of the velocity fluctuation of the lower plate. So, from this we can obtain the value of the characteristic length. As before, we can write the normalized velocity as a function of y divided by LC, t by Tc, and the parameter LC by under root nu Tc. So, the value of LC is obtained as under root nu by omega. And we can write this as a functional relationship for the normalized velocity. This is not a self-similar flow, since they are both y and t in this equation as independent variables. But there's still progress, in the sense we get to find out what is the penetration depth. This is the penetration depth, where this value is constant. As omega changes, this value of the penetration depth changes. Larger the omega, lesser is the value of y. Lesser is the value of the penetration depth. Here in this picture, this blue curve represents the velocity of the flow over the plate, and the red dots represents the particle motion, the location of the fluid particles at given time. We see a slight variation of this problem. In this case, the plate at rest, but the fluid above this is oscillating with a velocity v is equal to v naught sine omega t. The plate, being at rest, tries to slow down the fluid near the plate. Same formulation, unsteady forces, viscous forces, and the same value of pi. The functional relationship is also same. Here again, the characteristic time can be taken as 1 over omega, but there is no characteristic length that is available in the problem statement. So, we can use this parameter, that is this parameter, for defining a characteristic length, and that characteristic length would be clearly under root nu by omega, Tc being 1 over omega. This characteristic length is nothing but equivalent to the penetration depth, the distance above the plate in which the viscous effects can be felt. This is how the velocity profile and the particle motion would look like in this case. The blue line again, the velocity profile, is a distance like this. It would be LC, the effect within which the penetration of the presence of the lower plate is felt. That is, the viscous effects are felt. Above this, the fluid motion does not recognize the presence of the stationary plate at the bottom. One of a very serious problem in many countries is spoiling of cooked food in the absence of refrigeration or even power. One solution has been suggested for that problem. If we go down and store the food items in a cellar which is sufficiently below the surface of the earth, where the effect of the daily or yearly changes of temperatures are felt, the temperature at some depth remains constant throughout the day or throughout the year. The temperature at the ground level can be seen as a superposition of two cyclic temperature variations. One, the yearly cycle with the maximum temperature sometimes in June, and the other, the daily cycle of 24 hours with the maximum temperatures in late afternoon. This is for the northern hemisphere. We break the problems in these two parts and consider the two cyclic variations one at a time. The unsteady heat conduction problem is exactly like the Stokes' second problem. But here, instead of forces, we work with the heat currents. The unsteady heat accumulation, Q dot U, is given as rho V. V is the volume, rho V, which is the mass, C, the heat capacity, and del theta by del T as the rate of change of temperature. This gives us the scale factor for Q dot U as K rho KL cubed, which is Km for the mass, Kc, the specific heat, and K theta divided by Kt for the temperature gradient. Similarly, heat current through conduction is given as A times the heat flux, which by Fourier law is K del theta by del x, so that K Q dot K for conduction is Kk, the scale factor for thermal conductivity, times the area KL squared times the temperature gradient K theta divided by KL minus 1. That gives you Kk, KL, K theta. And from this should both scale factors should be same. We get LC square divided by alpha Tc as a pi number. Exactly similar formulation as in the last problem, except that due the kinematic viscosity here, has been replaced by alpha, the thermal diffusivity, which is K divided by rho C, thermal conductivity divided by density times the specific heat, alpha, the thermal diffusivity of the material. With this then, the normalized temperature differences, theta xt divided by theta naught, where theta naught is the amplitude of the temperature fluctuation at the surface, is a function of x by Lc, T by Tc, Lc by under root alpha Tc. Here again, we are given the characteristic time. There are two characteristic times in the problem. One is for the daily variations, 24-hour time period, and the other is for the yearly variation, 365 days as the time period. But there is no characteristic length. But as we have seen in the last examples, we can use this to find out the characteristic length. And what will be the interpretation of the characteristic length? The same as before. The distance through which the variation of temperature at the surface penetrate, the penetration depth. And the value of penetration depth is like under root alpha T. And then this is the functional relationship for normalized temperature difference. For soil, the thermal diffusivity is like 1.38 into 10 to the minus 7 meters square per second. For the daily variation of the penetration depth is 3.6 into alpha tau, where tau is 1 by omega, which is related to 24 hours daily variation. And this gives you about 0.4 meters or 40 centimeters. So the temperature below 40 centimeters would not change within a day. On a daily basis, they would be constant. And for the annual variation, the penetration depth is obtained as 7.56 meters. 7.5 meters. So below 7.5 meters, there are no temperature variations throughout the year. The temperature remains constant. This is some data I could find in literature. This shows the typical monthly soil temperature profiles. This is in a cold climate. So temperature is varying between minus 2 degrees Celsius and about 16 degrees Celsius. This yellow line represents the average temperatures in the month of January. This red line, the average temperatures in the month of June. The surface temperatures have changed that much. At depth of 4 meters, the temperature in June is lower than the temperature in January. And about 7 meters, they are the same. The 7 meters is about the same distance we saw in the last slide. The penetration depth of the yearly variation of temperature. And this shows the temperature variations, this gray line, the temperature variations in the month of August. The temperature has come down from the June temperature at the surface, but it is warmer than June at the depth of 4 meters. At 7 meters, all temperature variations are almost absent. So these measurements confirm the development that we did in the last slide. The above analysis has practical implications for constructions of buildings in Siberia or in Alaska, where the temperature throughout the year are very low. The ground is frozen in the winters, but when the sun shines in the summers, the temperature of air at the surface changes, becomes warmer, and so the soil begins to thaw. It gets hotter and it thaws, and it can no longer support structures. So foundations of the building must be dug to below the level till which the effect of the summer thaw penetrates. The layer beyond which the soil does not thaw is called permafrost. So buildings must be anchored in the permafrost. And in a calculation similar to that done in the last slide, we can find the depth of the permafrost for any given location. If at the onset of summer the ground can be assumed to be at a uniform temperature minus 20 degrees Celsius, and if the summer lasts for 100 days, when the average temperature can be assumed to be 5 degrees centigrade, find the depth to which the ground thaws. Given that the characteristic time is now 100 days, we can find out the penetration depth in the development that we did in the last problem. Let us now employ the concepts that we have developed to the development of boundary layer on a semi-infinite plate. A plate that starts at x equal to 0 and goes up to infinity to the right. Clearly, there is no characteristic length in the problem. There is no characteristic time in the problem. So, there is a definite possibility that a self-similar solution may exist. Functionally, the velocity u over the plate is a function of the two independent variables x and y, and of the parameters v naught, the upstream velocity, rho, the density of the fluid, and mu, the viscosity. It is convenient to work with stream function psi, which automatically satisfies the continuity equation. If we don't work with stream function psi, we need to deal with two dependent variables u and v. That complicates things. So we introduce stream functions. U is equal to del psi by del y, and v is equal to minus del psi by del x. This definition of psi automatically satisfies the continuity equation del u by del x plus del v by del y is equal to 0. So we only have to work with the momentum equation. Here again, we can write psi is a function of xy, v naught, rho, and mu. Within the boundary layer, viscous forces cannot be neglected as postulated by Prandtl. This means the inertial and viscous forces are important. So we consider these two forces. Inertial forces are like mass and the convective acceleration. Now we have used, after Prandtl, a different length scale in the x and a different length scale in the y direction. In the x and in the z direction, which is normal to paper, that's into the plate, the characteristic length is LC, and we use delta, the boundary layer thickness, as yet unknown, to be the characteristic length in the y direction. So the volume is now like LC square times delta. And the convective acceleration, which is like Vc times del V by del X, should be Vc times Vc divided by Lc, or Vc square by Lc. Viscous forces are like mu times Vc by delta. This is del V by del Y. Mu times the velocity gradient del V by del Y. So del V by del Y is estimated as Vc divided by delta. The area, which is not in the y direction, which is in x and z direction, is Lc squared. The resulting pi number is this. By equating the two estimates, both the forces are important, so they should be of the same order. So we can equate the estimates and obtain this pi number. Now, this pi number should be of the order 1. And if this is order 1, we can obtain delta by Lc in terms of Lc Vc by nu, which is nothing but Reynolds number. The normalized stream function is psi divided by V naught delta. Since u is like del psi by del y, so u is like del psi by delta. So psi by V naught delta is a function of x by Lc, y over delta, and this parameter, which is nothing but Reynolds number times delta square Lc square. There is no independent Lc, and we don't know delta. Let us use x, the local x location, as Lc. Then delta by x is like 1 over Reynolds number based on x. This gives you an estimate of the boundary layer thickness as a function of Reynolds number and x. And then the resulting functional relationship is psi divided by V naught delta is a function of y over delta. Using this in the momentum equation, we get this. An ordinary differential equation in terms of eta is equal to y divided by delta. If Double prime is the second derivative of f with respect to eta, and f triple prime is the third derivative of f with respect to eta. And this is to be solved with the boundary condition that f and f prime are 0 at eta is equal to 0. The stream function as well as the velocity at the plate must be 0. And far away, the velocity must tends to v naught. So u by v naught, which is f prime, tends to 1 as eta tends to infinity. This equation is not easy to solve, but the famous scientist Blasius had obtained numerical solution of this equation using hand calculators almost 100 years ago. Today, using MATLAB, this solution can be obtained in a fraction of seconds with a small program, a program of less than 10 lines. You can solve this, and this is the solution that we get. F prime, which represents the velocity u divided by v naught, is a function of eta. And eta was y divided by delta, and delta was like x divided by under root Reynolds number. So simplifying, we get eta is equal to y times under root u by nu x. Nu is the kinematic viscosity. This is f prime. This is a solution independent of x. So this is the velocity profile at any x. If we reduce the y coordinates and transform into eta by this transformation. We arbitrarily define the boundary layer thickness delta as a function where the value of u by capital U is 0.99. That is somewhere here. At eta is equal to 4.91, f prime is 0.99. And so we define the boundary layer thickness delta as 4.91x divided by under root REX. Many textbook gives a further approximation to this as 5x divided by under root REX. The second derivative of f, which would be the first derivative of u, which will be related to the viscous stresses. At the plate, the value of this is seen to be 0.332. From this, we can find out that the shear stress at the plate can be converted into a skin friction coefficient, which is equal to 0.662 divided by under root REX. This is valid as long as the boundary layer flow is laminar, which on a flat plate is up to Reynolds number is equal to 4 into 10 raised to the 5. Where have we made the assumption that the flow is laminar? The assumption is when we wrote the viscous forces by the Newton's law of viscosity, mu times the velocity gradient, which is valid only for the laminar flows. Note that in the boundary layer flow in a semi-infinite flat plate, there is no characteristic length in the x direction. So it is reasonable to suppose that the velocity profiles at various values of x are similar. If I want to find out if this is the velocity profile at this value of x, I can find out the velocity profile at a different value of x by simply squashing this in that direction, so that this length the boundary layer thickness is now reduced to this length. There is no change in length scale in the velocity. U by V naught same, but the y is scaled by delta. This is nothing but the manifestation of self-similarity. The velocity profile at a given location can be found out from the velocity profile at another location by simply scaling the velocity profile. In this case, only in the y direction. At another value of x, the velocity profile is obtained by further scaling. These three profiles are drawn by simply stretching or collapsing in the y direction. There is another way to interpret self-similarity. We can consider the velocity profile at this location and the velocity profile at this location as two different experiments on the same plate with the same uniquity parameters. And if we do this, the velocity profiles are similar. Location exchanges, so the scale in the y direction changes. Self-similar solutions are of great significance in many applications. In almost all such applications, the common factor is that there are no natural characteristic quantities of the two variables involved. And so the characteristic quantity of one variable is determined in terms of the value of the other variable. It is not just on the flat plate, but flow over wedges are also self-similar. Khan obtained the conditions under which the flow could be similar. And he said wedges, flow over wedges is one case where the flows are similar. That is, the profiles that we get at any x is similar to the profile that we get at another x. Flat plate corresponds to the case beta is equal to 0. This wedge with beta between 0.5 and 0 is a flow in which the fluid is accelerating. This is for beta is equal to 0.5. This is the case when the flow is against a flat plate. The value of beta between 0.5 and 2, the flow reverses in this. This is also a flow in which along this surface the flow would be accelerating. This diverging flow, on the other hand, for beta negative, is the case where the flow is decelerating. And as we studied in the last lecture, the flow tends to separate when the flow is decelerating. Let us see, can we get this information here? So Khan says that if there's a wedge with angle pi beta in there, then the velocity as a function of x can be written as v naught times x raised to power m, where m is beta divided by twice minus beta. So for m positive, the velocity is increasing in x direction. For beta less than 2. We introduce a variable eta is equal to y under root m plus 1 divided by 2 times u by nu x, or which is the same as this, And if we get this equation, an ordinary differential equation of one dependent variable f and one independent variable eta. And this has to be solved with three boundary conditions: f and f prime is equal to 0 at eta is equal to 0, and f prime tends to infinity as eta tends to infinity. This is the kind of profile that we get. This is the edge of the boundary layer on the upper surface. This is the velocity profile within the boundary layer. And these are those profiles for different values of beta. This green line is for a flat plate when beta is equal to 0. And we have discussed that case just now. This is for the converging flows where the flow is accelerating. These are the cases where the flow is accelerating. This is also a case where flow is accelerating. For beta positive, we see the gradient of f at the wall changes, it increases. But this set of curve represents the negative value of beta. This is for beta is equal to minus 0.1. This line is for beta is equal to minus 0.18. And this line is for the value of beta as minus 0.1981. What is the significance of this value? This is the value when the shear stress at the wall reduces to 0. That means the gradient of velocity at the wall becomes 0. Any further decrease in the value of beta would result in a reversed flow. So this line, this last line here, is what represents separation on the surface. The boundary layer beyond this separates. So what is self-similar about it? Let this represents the growth of boundary layer. If this is the velocity profile at this location, then this velocity profile at this location, it has been obtained by simply stretching this velocity profile both in this direction as well as this direction. Stretching in this direction to match the boundary layer thickness here, and stretching in this direction to make the velocity at the edge of the boundary layer match with the inviscid solution at this location. Similarly, at this point, this velocity profile, and this velocity profile, all velocity profiles are self-similar. Anyone can be obtained by scaling another profile linearly. Let's give one more example, the example of Trinity explosion. Trinity was the first test of a nuclear device conducted by the USA. Slightly after the bomb in Hiroshima, the US authorities released a sequence of still shots which contained both the time stamp as well as the scale. So you could measure from this that at time t is equal to 0.016 seconds after the explosion, This is the diameter of the fireball, and this diameter can be scaled in terms of meter using this mark of the scale. After the war, a famous British physicist, Professor G.I. Taylor, estimated using this picture the yield of the bomb. There was no other data that was used. He did not have the information of what the yield is. Using self-similarity alone, he estimated the yield. Two assumptions needed to be made: that the energy E of the explosion was released in a very small scale, and that the shock wave that came out, the fireball, was spherical. Now from this picture, we have size of the fireball as a function of time at several different times. The radius of the fireball should depend upon the energy E, the time t after the explosion, and the density of the surrounding medium, which is air, the initial density of air. Since there are no length scales and time scales involved in the problem, there is no parameter which contains any length scale or time scale. We may take the current time t as a characteristic time and express the characteristic length in terms of this time t. The scale factor of energy would be like scale factor of mass times the scale factor of velocity squared. This is like kinetic energy, and K mass is like K rho KL cubed. Kv square is replaced by KL square divided by KT square, so that this becomes K rho KL5 KT square. Visualize a picture at two different times to be as if there are two different experiments in a fashion similar to what we discussed in the last example. And since it is the same explosion, Ke is 1, and from this we get KL5 into KT minus 2 is equal to 1. That is, R should vary like t raised to power 2/5. At time t is equal to 0.006 seconds, the radius of the shock wave was approximately 80 meters. This is the diameter. So the radius you reduce to radius is 80 meters. And at time t is equal to 0.016 seconds, it is 105 meters. From this, Professor Taylor estimated the yield to be 10 to the power 14 joules. 1 kilogram of TNT is energy equivalent to about 4 megajoules. So that 10 to the power 14 joules is about 25 kiloton of TNT. The actual yield was 22 kiloton. So that should convince you of the power of similitude analysis and self-similitude. Thank you.